Okay, so I just want to give you a little example here. If you watch the YouTube video, this is the one I use in my YouTube video on this. Talking about making a very cheap, pathetic cheese sandwich that only has one slice of cheese. But let's imagine you're going to make a cheese sandwich that only had one slice of cheese. And okay, so our ratio then, or our quote unquote balanced equation is 1 cheese plus 2 bread yields 1 sandwich, right? Just like any other equation, right? 2 to 1 to 2 to 1. Ours is 1 to 2 to 1, right? Okay, so does that same ratio work for masses? Could I say a pound of cheese plus 2 pounds of bread gives 1 pound of sandwich? Of course not, right? Yeah, so these ratios, it's not 2 grams makes plus 1 gram, right? The ratios are always pieces, particles, right? So same things here. Here are pieces where we're using moles, 2 moles to 1 mole or whatever. Here we're just using actual particles, like pieces of cheese, pieces of bread. Okay, so let's say I had this. 3 slices of cheese, 8 slices of bread. How many sandwiches could I make? 3. You're very quick on that. Remember how easy that was for sandwiches. I promise, it's no harder when it comes to chemistry. You just want to make it harder. So, okay, there you go. You're exactly right, making 3. So which of those 2 reactants, cheese and bread, did we have an excess of? Did we have more than we needed? Bread, yes, we had extra bread. So bread, the reactant we had more than we needed of, is called the excess reactant. Which reactant then did we run out of? That we run out of then that limited us to only making 3 sandwiches? Cheese, right? Right. So cheese is called the limiting reactant. Okay, it's the same way in chemistry. If you do not have the exact right amount of lead 2 oxide and tin 4 carbonate, then one of them is going to run out first, and you're going to have extra of the other, unless you have the exact 2 to 1 ratio. So yeah. If I had 4 slices of cheese and 8 slices of bread, it would have been perfect, right? But I did it. It wasn't the exact 1 to 2 ratio. Same thing in chemistry. If it's not the exact 1 to 2 ratio, then you're going to run out of one of the reactants first, and that's going to stop how much products you can make. Same thing here. Cheese ran out, and it stopped us making more sandwiches. That makes sense? So it's the exact same way. But again, it's all based off the pieces, right? So not the mass. We've got to think about it in terms of the pieces, the moles in our case. Okay. So the reactant that was completely consumed, that's called the limiting reactant. Because again, when that one runs out, it limits how much product we can make, right? How many cheese sandwiches we can make. So the one that runs out first is the limiting reactant. The other way to think about it then, sometimes, is the one that gives you the least amount of potential product is the limiting reactant. There's enough cheese to make 3 sandwiches. There's enough bread to make 4 sandwiches. So the cheese made the least amount of potential product, so the cheese was the limiting reactant. The other one, the bread, was the excess reactant. Are you with me? Okay, so let me just try this with a chemistry example. Another 2 to 1 ratio here. So for every 2 hydrogens, I react with 1 oxygen, and now I make 2 waters. So let's say, how many moles of water could I make if I have 6 pieces of hydrogen and 4 pieces of oxygen? Now, it's not cheese and bread, it's hydrogen and oxygen, but it works the exact same way. So let's just kind of work through it here. Let's try it. So if I have, I'm just going to write 6 moles of hydrogen. Okay, so how many moles of water could 6 moles of hydrogen make? Well, I'm trying to relate 2 different things, so we know we use the mole to mole ratio. So what's the relationship between hydrogen and water?
2 to 1.
Hydrogen and water. 2 to 2, right? Okay, so right. So for every 2 moles of hydrogen, I would make 2 moles of water.
That's a 1 to 1, though. 2 to 2, essentially.
Yeah, same thing, right? So I'm going to make, so I can make 6 moles of water from the 6 moles of hydrogen. How about the 4 moles of the oxygen? What's the relationship between oxygen and water? 1 to 2. Right. So for every 1 mole of oxygen, I can make 2 moles of water. So I can make 8 moles of water. So you can see here then there has some potential. There's enough hydrogen to make 6 moles of water. There's enough oxygen to make 8 moles of water. How much water will I actually make? Will I make 6? Will I make 8? Or will I just add them together and make 14? I make the smaller amount, right? Same thing as the cheese and the bread, right? So I can't keep going. So yes, I'll actually make 6, right? Because why can't I keep going and make 8? There's enough oxygen to make 8. Why not? Why can't I keep going? Because I need more what? Yeah, yes, right, exactly. So I need both hydrogen and oxygen. And what happens then once I get to 6 moles of water? What happened? There's still plenty of oxygen around, right? But I ran out of the hydrogen. Does that make sense? So when I get to 6, the hydrogen's all used up. There's enough oxygen to keep going to make 7, 8, but the hydrogen ran out. Okay? So yeah. So how much we're going to make? We're going to make, actually said we're going to make 6 moles, right? We're going to actually make 6 moles. So which was the limiting reactant then? Which one limited us to making only 6 moles? The hydrogen, right? Perfect. And which was the excess then? That was the oxygen, right? Perfect. Okay. Okay, so that's all you do. So we're going to do the same thing like I did here, but I'm going to do it twice. So for example, I would turn this one into a product and this one into a product. Whichever one gives you the smaller amount is the amount you'll actually make, because you can't make both. You can only make whatever the smaller the amount is. Okay? Okay. So let's just try another example here. Let's say I have 25.0 grams of this and 25.0 grams of this, and it wants to know how many grams of iron will I make. So let's just start writing this down. So 25.0 grams of this, 25.0 grams of this. The question is, how much of this will I make, right? So I'm going to have to do that reaction twice. I'm going to say, okay, 25 grams of iron 2 oxide, how much will that make of iron? And the 25 grams of aluminum, how much will that make of iron? We'll get 2 answers, and which one will I choose as the right one? The smallest one, right? The smallest one. And whichever reactant gave me the smallest one was the limiting reactant. The one that gave me more was the excess reactant, right? Okay, so let's just try this together. We'll work it out. And again, this is pretty important if you want to do this kind of stuff, because it's better, obviously, you know, in the real world, if you have the exact amount, and then you're not wasting chemicals, you have extra chemical you're not using, spending money. So it's better if you can get the exact amounts. So let's just see. 25.0 grams of FeO. So let's do that first. Like I said, let's turn that into the iron. So what's the first thing I have to do with the grams of FeO? Molar mass, right? You see mass, you should be thinking, oh, molar mass. So add up an oxygen and an iron. I think it's 55 and 16, it'd be 71.85, I think. Double check me. But okay. Now I'm in moles of FeO. But I'm trying to get to what? What's my goal? Grams of what?
Molten iron.
Just iron. So I'm trying to turn FeO into Fe. So how do I relate FeO to Fe? Yeah, which is, what is it here? What is it in this case? Yeah, 3 to 3. Yeah, 1 to 1, but 3 to 3. So I was going to just put 3 to 3 just to use the actual ratio. So for every 3 moles of FeO, I make 3 moles of Fe. Perfect. Okay, yes, so now I have moles of iron, and you said I wanted the mass in grams of iron, so what do? Molar mass. So find the mass of iron. It was 55.85 grams per mole. So let's punch that in our calculators and see what we get. I'll let one of you do that for me and tell me what you got. Let me just think about the sig figs while you're doing that. So this will be 3 sig figs. This will be 4. This is exact, because these are counting numbers. This is 4, so the fuse will be 19.4 grams. Okay, so that's the first possible answer. Okay, now let's do it again for the aluminum. So same thing. Now let's turn the aluminum into iron and see if it gives us the same number, a bigger number, a smaller number, whatever. So what's the first step? Grams of aluminum. Molar mass. Yes, so think aluminum's 26.98. That's the mass of a mole of aluminum. Okay, now I'm in moles of aluminum. What do? Mole ratio. We got 2 to 3. For every 2 moles of aluminum, I make 3 moles of iron. So let's put that in here next. 2 moles of aluminum, 3 moles of iron. And then I got moles, I want mass, so we'll use molar mass. 55.85 grams is 1 mole of iron. So 77.6. So I have enough iron 2 oxide to make 19. I wonder how long it's been paused. I know, I can't make that go away.
Oh no, I think that the 8 just popped up. So
yeah.
Maybe it affected it.
I don't know. So we have, let's see what we got. We got 113 grams of aluminum. Okay, 113 grams of this. And we got 279 grams of this. And the question is, how many grams of iron will we make? Awesome. So, we're going to do the same thing. Okay, get this stupid thing off here. So we're going to do the same thing. We're going to turn aluminum into iron. We're going to turn iron 3 oxide into iron. Yes, I got it. You kidding me? I'm sorry. You'd think a computer would be smart enough to not load that crap while you're in the middle of a presentation. Drives me nuts every time it does it. Okay, so let's just try it out here. So we're gonna do it twice. We're gonna turn aluminum into iron. We're gonna turn iron 3 into iron. We're gonna pick the smallest, right? So let's just do it. So 113 grams of aluminum. So what do I do first? Molar mass. So aluminum is 26.98 grams per mole. Okay, what's next? Mole to mole ratio. So what is the ratio between aluminum and iron? 2 to 2. So 2 moles of aluminum makes 2 moles of iron. Awesome. Now I've got moles of iron. So what do I do next? Yeah, it wants to know the mass, so use the molar mass. So iron is 55.85 grams per mole of iron. So what's that one give you?
234.92.
How much?
234.92.
234?
230. Yeah, sorry.
Okay. Let's do the other one. 279 grams of Fe2O3. So we got the mass. We're going to do the molar mass. So out of 2 irons, 3 oxygens. What is that? 150? 100 and what? 160?
59.7.
That sounds better. 59.70 sounds right to me. So what do I do next? Multimole ratio, and for every 1 mole of Fe2O3, we produce 2 moles of Fe. Okay, now I'm in moles, I want to be in mass, so molar mass again. So how much do I actually make? 195 of iron. So if I mix these 2 powders up, how much molten iron would I actually make? Pick the smaller one, right? 195. Excellent. Right. Any questions? So, which reactant was the limiting reactant? This one here, right? This one. This was the limiting reactant here. What was the excess reactant? Aluminum, right? Perfect. Okay, your turn. Why don't you try this one? This is something here, something from the world of fashion and textiles. It's how you make a fabric called acrylic. You know, acrylic sweater, acrylic sweater, or scarf or something. So what they do is they take propylene and react it with this stuff, nitrogen monoxide, and they make this stuff, acrylonitrile, which then goes on to make synthetic fibers called acrylics. So write down the reaction there at least, and then I'll give you the whole problem here. Okay, get that reaction written down? Or do you have the handouts on the handout too? It's even the easier way. Hope you have the handout in front of you. Okay, so let's look at it. It says if you have 21.6 grams of propylene and 21.6 grams of NO, how many grams of acrylonitrile will you make? So try it out. Help each other out. Ask questions. Ask me questions. Well, in case you're wondering, the guy that was coming isn't coming, obviously, today. I forgot to tell you that. I think he's coming next week. So, try it out. I think you guys got it, but just in case. So help me out here and just give me the numbers to make it faster. But so 21.6 grams of C3H6. Use a molar mass 3642.09. And then for every 4 moles of C3H6, we make 4 moles C3H3N. Let's see, so the molar mass of that would be 391453.07. Something like that.
Yeah.
And that one gives you what?
27.
That one's 27.2 one? Okay. I should write grams in there, but don't really have too much room. There we go. Okay, so let's do the other one. 21.6 grams of NO. 30.01, I think. 14 and 16 is 30, yeah. And then that is 6-to-4 ratio, right? So 6 moles of NO, 4 moles C3H3N. Same molar mass. I was going to put ditto here. And that was 25.5. So yes, then you pick the smaller one, right? Okay, questions on that? Okay, again, there's several videos on this, so go watch them if you're still confused. If you need a little practice, you know, try it out. There's practice exams too, right? Try those out. Go to the tutorial center. Email me. Ask lots of questions. There's practice quizzes. There's practice exams. There's practice problems on mastering. Lots of things to practice on. Okay, so the number we just calculated, that's the amount you would make theoretically if everything went perfectly. But of course in the lab, you often do not make 100% of what you plan to make. You know, things happen. You spill something, doesn't heat quite long enough, whatever. Your beaker was dirty, something. So we often refer to what's called the percent yield, which is the percentage you actually got out of what you should have got. So when you go in the lab and you measure out your actual product, well, the amount you actually made is called the actual yield. And the amount then that you calculate you make, like we did here, calculated, that's called the theoretical yield. So that's how much we should have made. So then the percent yield is just the actual yield, the amount you actually made, divided by the theoretical yield, the amount you should have made if it all went perfectly, times 100. So your percent yield might be 95%. So you actually got out 95% of the amount you should have got. Or it was 12%, and you really had a bad day in lab. Whatever it was. It's the amount you actually made over the amount that you calculated. So all these things here we just found, those are all theoretical yield. Because theoretically I should make that. Of course, again, in the real lab, things happen, right? You might get 99%, but probably not a perfect, every last atom doesn't quite make it where it's supposed to all the time. So you have the percent yield. So actual over theoretical times 100. Actual over theoretical times 100. Actual over theoretical times 100. You got it. Okay, so let's just give an example. Let's just say you did this reaction, and you calculate you're supposed to make 0.988 grams. That's your theoretical yield. But you run it, and then you weigh your product, and you actually only made 0.875 grams. So what's your percent yield? Well, you would take the actual 0.875 divided by the amount that you calculated, the 0.988 times 100. 88.6%. Yeah, so in that case, your yield will be 88.6%. So you got a 88.6% yield, you would say. So we got, that much what we should have gotten. Not bad. Now, in theory, of course, you can't really have yields over 100%, but sometimes it does happen. Which seems crazy. It doesn't actually mean that you somehow pulled matter out of your butt. Normally what it means is there were like some side reactions were going on, and you actually wind up with a little bit of the tin-4 carbonate left in here too, and it weighs a little more than that does, or something like that. But you should always have, normally, less than 100% seems reasonable. But yes, sometimes I've had a lab where you get the result back and it's 140% just because the product maybe the product then and then the product then was filtered through water, and it wasn't dried all the way, and there's still water left in it, so it makes it weigh a little heavier or things like that. But ideally, it should be, of course, less than 100%, because you can't just create matter out of nothing. So, okay, so let's try one here. Let's do the whole shebang here. Let's balance an equation. Let's do the calculations. Let's find the percent yield. So, first off, try that out. How would you balance it? Think about that. Talk it over with your neighbor. How would you balance it? 1, 5, 3, 4. Let's see. That gives me 3 carbons on the left, 3 on the right, 8 hydrogens on the left, 4 times 2, 8 on the right, 5 times 2, 10 oxygens on the left, 3 times 2, 6, plus 4 is 10 on the right. So good. 1, 5, 3, 4. Okay, carry on. Do the next part. Keep going. Time. So, what are your 2 answers you got to it? So, what'd you get? Write down the answer. So, 5 grams of C3H8. How much water did that give you? 8.17 grams. Everybody agree with that? And how about 20.00 grams of water? How much did that give you? 9.01. Okay, good. So what's the answer? What's the actual theoretical yield? The small one, right? The small one. Okay. 8.17. 8.17. So, what's the percent yield? Well, we would take the actual yield it gave us, 6.21, over the theoretical, the one you just calculated, 8.17 times 100. And what is that? 0.0? Looks like 3 sig figs to me, that's why I'm asking. Okay. Okay, well, let's talk about our last little topic here. Talk a little bit about energy and making reactions happen. And then we'll wrap it up for the next 20 minutes. So there's 3 things that got to happen for a reaction to occur. And they kind of make sense when you think about it. So you've got your solution, your molecules are on there swimming around. First thing they got to do is they got to actually find each other. They got to connect. They got to collide in order for a reaction to happen. They can't just react from across the beaker. Second thing, they have to collide the right way. The orientation has to be on. So if you're trying to make a nitrogen-oxygen bond, well, the nitrogen-oxygen have to actually hit. It can't hit with the back of the molecule. You got to hit the right way. So the orientation is next thing that's important. And then they have to have sufficient energy to actually drive the reaction. So this is called the energy of activation. So it's kind of like, let's say it's kind of like you have 2 Legos, and you're trying to put Legos together. We can't just snap them together however you want, right? They only have a certain orientation that makes them snap together. And then you also have to give them then enough energy to actually, snap them, because if not, they will just kind of, they won't actually stick. So it's the same thing. They got to collide. They got to collide the right way, and they got to collide with enough energy. So that's the 3 things that got to happen when molecules are trying to react. So those are the big words: collision, orientation, and energy. So all of this ties into something called the activation energy, which kind of tries to take all of these things into consideration. I'm going to have to go on so you can go back to PowerPoint later if you need to, or watch the video later. But so the activation energy, that is the amount of energy required to then take and break apart these bonds, let's say, and then put them back together in products. So we got to break apart connections and then reform new connections. So the amount of energy it takes to break them apart and kind of get the ball rolling, that's called the activation energy. Okay? So if the energy of a collision when they're bouncing around is less than that, then nothing happens. It just bounces off and they keep swimming around. So they got to hit, again, with enough energy and the right orientation to actually push it over the hump, if you will, of the activation energy. Okay? So, normally, most reactions, there are millions of collisions occurring, but again, many of them are just far too easy, or they're not hitting the right way, so the reaction doesn't occur. So we've got to have all three things aligned perfectly for the reaction to happen. Okay, so let's look at a picture here. So this is what you might, so this is kind of the thing you might see. So reactants on the left going to products. So there's two cases. There's one case then where the energy of the reactants, what's inherently stored up, the potential energy of these bonds and everything, and these connections, is greater than the energy stored up in the products, or vice versa. The energy in the reactants is less than the energy of the products. So regardless, in order for me to get from the reactants to the products, it's not just a straight downhill. I have to put enough energy, remember, to break those things apart. So that's this little hump here you see. So that hump, from the starting point to the top, that's called the activation energy. That is the actual activation energy. And you often see that abbreviated as E sub A for activation energy. So, when the energy of the products is less than what you started with, well, that means between here and here, it must release energy. Because let's say here it was 100 and here it's 50. Well, it had to lose 50 along the way. So if it loses energy, that's called exothermic. Exothermic. Did we already mention exothermic in the past? Yeah. Did we not? I can't remember. We did? Okay. So exothermic is when you lose heat. Heat is exiting. And the other case is, the energy has to actually go up. So it has to gain energy. And that's called endothermic. So exothermic, energy is lost. Endothermic, energy is gained. Or heat. You can say heat is lost. Heat is gained. Exothermic heat is released. Endothermic heat is gained or absorbed. Okay, so we won't spend a whole lot of time on this, but I just want to show you. I'm going to skip past this. This is what I just basically said. Where do we go here? So, what you can do is you can measure what was the energy of the products, subtract the energy of the reactants, and that gives you what's called the change in the enthalpy, or the change in the heat. So, if that number, delta H, is called enthalpy, if that number is negative sign, delta H negative, that means it was negative, it lost heat. So that's exothermic. So when delta H is negative, it means it was exothermic, heat was released. So when that difference between those two is negative, delta H is negative, that means exothermic, heat is released. I'll say it 5 times because I don't see very many pencils moving. When delta H is negative, that means it's exothermic, heat is released. The opposite, when it has to go uphill, the delta H will be positive. For example, this reaction, delta H is positive 180. So that means it has to absorb energy to go from here to here. So that would be endothermic. So when delta H is positive, it's endothermic. Delta H negative, exothermic. Delta H positive, endothermic. So negative, heat's lost. Positive, heat's gained. Okay, so every reaction has an enthalpy. Every reaction either takes heat or else it loses heat, every reaction. So that's called the enthalpy. So for example, here's the combustion, we saw this before, of propane. I showed you this reaction before. This is propane. So when you combust propane, it reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. And when it does that, it releases negative sign, exothermic, negative sign, it releases 2,044 kilojoules of heat. So, that value, that delta H, the enthalpy, the amount of heat, that is for this equation as written. So what I mean by that is every 1 mole of propane produces 2,044 kilojoules. Or every 5 moles of oxygen is 2,044 kilojoules. Or every 3 moles of carbon dioxide, every 4 moles of water. It's for this reaction. If I had, let's say, 2 moles, then I would get out twice the heat. Or if I had 5 moles, I would get out 5 times the heat. Are you with me? So it's for this reaction as written. So think of it like, oh, it's negative 2,044 kilojoules per 1 mole of propane. If I was doing it, let's say, for oxygen, oh, negative 2,044 kilojoules per 5 moles of propane. So you can just write a little conversion factor in there using that enthalpy. Okay? So it's always for the reaction as written. And there's books full of these tables of all these reactions that have been studied, and they've measured all the heat. And you can do some interesting things with it. But as I always say, come back in 110. We'll show you interesting things you can do with heat of reactions. Okay, so let me show you an example here of what we can do. So let's say how much heat would be evolved if I burned 13.2 kilograms of propane. So this is a handy thing to know. You know, you want to burn something. You want to make sure that your reaction then won't be like too hot. You know, to melt the container or whatever it is. You know, melt your engine. So you got to monitor all this stuff. So let's say 13. Try that again with my smaller pen. 13.2 kilograms of propane. So I want to know how much heat, how many kilojoules of heat will I give off? Well, the kilojoules of heat, it's 2,044 kilojoules per 1 mole of propane, but I'm not in moles, I'm in kilograms. So what could I do to get me towards moles? Yes, molar mass. First, one other thing first. First, let's turn the kilograms to grams. Yes, and then we'll do the molar mass. So kilogram. The molar mass of propane. 3 times 12, 16, 36, and 8, 44. So this part's all the same. Now I'm in moles of propane. Right, so this part here you know how to do. I'm going to turn it into kilojoules. How do I do that? Oh, there's 2,044 kilojoules per 1 mole in this case, right? If it was oxygen, I'd have said per 5 moles. If it was CO2, I would have said per 3 moles, right? It's right off the coefficient, so. Right, 1 mole, because this is 1 mole, right? Okay. So you could work that out. I think I already did. I got negative 6.12 times 10 to the 5th kilojoules when I did it. So there you go. That's how much heat you would give off if you burned 13.2 kilograms of propane. Okay, let's look at a couple examples and we'll wrap this up. Got that written down? Okay. So, let's do a little rocket science. Let's say you're part of the Apollo mission and you are going to use hydrazine as your fuel and you're going to combine it with dinitrogen tetraoxide. And you know you're going to burn 273.9 grams of hydrazine in one certain stage, but you want to make sure that it won't give off too much heat and fry the astronauts or something. So let's see. So how much heat would 273.9 grams of hydrazine give off? So let's just try this sucker. So 273.9 grams of hydrazine. I'm going to turn that into heat. So what do I got to do first? Molar mass. So let's add up 2 nitrogens. Those are 14. So 2 times 14 is 28. Plus 4 is 32. 32.06. Okay? So that's the moles. I want to know the heat. How do I relate the heat to the moles in this?
2
Yes, every 2 moles of hydrazine produces 1,049 kilojoules. So I would put 2 moles of hydrazine on the bottom. Again, not 1 now because of this 2 over here. Negative 1,049 kilojoules. Well, punch that in for me. Let's see, we got 4 sig figs, 4 sig figs, 4 sig figs. So it should be 4 sig figs. Looks like. Got an answer? Don't forget to divide by 2 at the end. What's the answer? Somebody. 4,400 and what? 81. Anybody else get that? Awesome. Okay. Running out of time. I'm going to do the next one. Negative 4,481 kilojoules. Everybody got that written down? I want to do one more. We got 5 minutes. This is our. Okay. Have any veterans in here? Okay. MREs, your favorite thing ever, probably. So, MREs use an exothermic reaction. So you take your little pouch, you pour in the water, gives off lots of heat, put the food inside, it cooks it. Here's the reaction they normally use. Oftentimes, not all the time, but a lot of them use this reaction. It's an exothermic reaction. It gives off 353 kilojoules per every mole of magnesium or per every 2 moles of water. So let's figure it out. Let's say you pour in that bag 25 grams of water. How many kilojoules of heat would you produce? So, got 4 minutes. Figure it out. .0 grams of water. Oh, and I have a quiz to pass back. Do it real quick. Yes, but all known with good reason. Okay, talk it over. What'd you guys get? We got 2 minutes here. What'd you guys get? Negative what? 240. Negative 240? 245. Looks like 3 sig figs, 1.0. Negative 245. Everybody getting that? Anybody not getting that? Need me to work it out? Oh. Okay, so when I see you on, what'll it be, Tuesday, we'll have our test on 3, 5, and 6. So bring a little short Scantron, science calculator. Again, you have, we got Friday, Saturday, Sunday, Monday study. So I said, so again, there is a practice test, but I encourage you to use that practice test after you study and you feel like you're ready. Then go ahead and print it out and actually, try the test the way you would and see if you're really ready. And then if you're not, then on Monday, come see me. Go to the tutoring center and get some help with whatever you miss on that test. But there's also practice quizzes on mastering. There are also extra practice problems on mastering, remember? As well on mastering. And there is also on Blackboard, there is that whole section on the naming practice activities, right, you can do. So yeah, do all that. Plus there's the YouTube videos, all of this kind of stuff that I put together. So I'll do that real quick before you go. Lauren. I will post the answer keys for these, so you can go over these once you try them out, all the naming ones. Did I not get a naming one on Tuesday? Anybody not here Tuesday? You didn't get a little lovely 8-10 page practice thing? That was one else. Two more? Right.
Can I get it? Thank you.
10. It was just one each. Yeah, one each, yeah.
I thought it said 20 on mine.
Oh, so 20?
Online it says 20.
Yeah.
Oh, mine said that originally, but I think I changed it when I actually put the grades in.
I'm okay with it.
You have one of these?
I was wondering if you had another one of these so I can pop it in.
I don't have one, but you can ask somebody. Maybe they can write down.